Hello. Previously, we were discussing one important. So, hello. In the previous lectures, we were discussing infinite deep square potential well. In today's lecture, we are going to see the impact uh, of expansion of the well. That is what I want to infer that what if your well expands? Okay, so this is the theme of today's lecture. Okay, today's lecture is about the expansion of the well. So uh, let us understand this concept using an illustration. So let us consider a particle of mass m. So there is a particle of mass m, and which is uh, in an infinite deep square potential well. So let us consider a particle m in an infinite deep square potential well. Now, what happens is, in a moment of time, it so happens that your well, which was initially having width a, now goes now actually transforms into a well with width 2a. Okay, and let us assume that case, in this particular case, the wave function momentarily remains undisturbed. Let us assume that wave function momentarily remains undisturbed, and let us assume that initially, I mean, when your well was having width a, initially uh, this particle was in the ground state, was in the ground state. Now we want to find that if energy is now measured, and we want to find what is the most probable result. What is the most probable result? Okay, so we find where will we find the particle? Will it remain in this ground state in the new well also? Will it not remain in the ground state in the new well? So on and so forth will be our uh, thinking. First thing to understand, whenever a wave function initially was in state psi I, and now it goes into psi f. Okay. So what is the probability? What is the probability? How would you find? You'll find using Cn mod whole square. And what would be Cn mod whole square now? It will be psi f, psi I, and this mod whole square. This has been covered in the postulate section. So if your initial wave function is psi I, and now the particle goes in a final state, that is psi f, what is the probability of getting the energy measurement in EF? So that would be simply Cn mod whole square. Okay. So I hope it is clear. Uh, Now, for this, we'll have to first find Cn. Now, a few things first. When you are in the new well, what are the new allowed energies? So now new allowed energies will be n square, pi square, h ket square upon twice ma 2a whole square. And what would be the new eigenfunction? So new eigenfunction would be simply root over 2 upon 2a sine of n pi x upon 2iz. Okay, this is another thing. Now, what would be Cn? Cn would be integration from 0 to a psi n star and psi initial integral. This thing. Okay. I know what is psi I. So it is integration from 0 to a sine of n pi x upon a into sine x, sine pi x upon a dx. And here you will get 2 upon root 2 upon a, and another you will get root over 1 upon a. Okay. So this will become, I think, root over 2 upon a, integration from 0 to a. Let us multiply it with 2 and 2. So I'll get simply 2 sine a sine b. And I know what is 2 sine a sine b. I can write it in terms of cos now. This will become cos of a minus b upon 2. So if you remember, I'm writing it here so that you don't forget. Sin a, sin b is cos of a minus b minus cos of a plus b. Okay, so this is twice, sorry, this is twice. Okay, so final state is root 2 upon 2a sine of n pi x upon 2a. Okay, so this will become, okay, cos of, I hope it is clear. And now, if I want to integrate this, this will come out as root 2 upon 2a integration of sine of n by 2 minus 1 pi x upon a divided by n by 2 minus 1, and sorry, this is pi upon a and minus sine n by 2 plus 1. This is pi x over a divided by n by 2 plus 1 pi upon a, from where to where? From 0 to a. And remember, if I place n equals to 2 here, then this will give me a problem. So I'm not using n equals to 2 here. Okay, so I'm not using n equal to 2. We'll find that in other case. Okay, so in this particular scenario, I cannot place n equal to a 2 because otherwise it will blow up. So what would be Cn? Mind you, we are doing it for all n not equal to 2. So this will be equals to uh, root 2 upon 2a. So I'll write it as 1 upon root 2a. And now let us place all these values. So if I place a here, so it will go to not 0. Remember, there is some fraction here. So you have to write it n upon 2 minus 1. If I place 0, then it is certainly 0. So that's not a worry. We'll have to see the cases. Okay, don't worry. Minus sine of n by 2 plus 1 into pi divided by n by 2 plus 1. Um, this will remain, I think, this pi upon a will remain. So pi upon a remains here, pi upon a remains here. Okay. At 0, both are 0, lower limits are 0. The upper limits I've kept it. See, if n upon 2 minus 1 becomes an integer, then this will become 0. So let us try to find. This a cancels. So now you're going to have this thing, that is Cn uh, is nothing but a little bit of things, 1 upon root over 2 pi, and this would be sine of n by 2 minus 1 pi upon, let me write it as n minus 2, 2 goes over, so here you'll have a 2. Okay, it is fine, I think. I'll not write 2, I think it's better not to write 2 right now. So I'll write 2 here only, minus 2 times sine of n by 2 plus 1 times pi divided by n plus 2. Okay, so this is one thing that we've got. So now we know. Okay, now see, what I can do is a little bit of mathematics I'll do here. So just think about this bracket. Okay, just think about this bracket. And you already know sine of theta is equal to sine of 2 pi plus theta. Okay, okay. If I place instead of theta this, so sine of n by 2 pi minus pi I can write it as sine of 2 pi plus n by 2 pi minus pi, and it becomes equals to sine of pi plus n by 2 pi. So it is equivalent to writing sine, if I take pi common out, it is n by 2 plus 1. So whether I write this and this, these are both same things, because sine theta is equal to sine 2 pi plus theta. So Cn becomes 1 upon root 2 pi. I'll take this common out. These both are same. So basically I'll write sine of n by 2 plus 1 pi. And you'll get, so 2 also you'll get outside. So 2 is here. If I'm not wrong, 2 will come out, right? Okay, that is not a worry. And this is 1 upon n minus 2 minus 1 upon n plus 2. So this will give you 4. So Cn would become what? Cn would become, this is 2, this will give me 4, 4, 8, 8 upon root 2 pi sine of n by 2 plus 1 pi, and this will give me 1 upon n square minus 4. Okay, and you can do rationalization here. So if I rationalize it, I'll get simply 4 root 2 upon pi, and then I'm getting sine of n by 2 plus 1 pi times this entire thing times 1 upon n square minus 4. So now Cn I'm getting equivalent to, see, if n becomes even, even upon 2, it will give me 2, 2 plus 1 is something 3. So if n is even, so let's say just take n equal to 2. If I take n equal to 2, 2 by 2 is 1, 1 plus 1 is 2, sine 2 pi is 0. If I take n equals to 4, 4 by 2 is 2, 2 plus 1 is 3, sine 3 pi is 0. If I take 6, 6 by 2 is 3, 3 plus 1 is 4, sine 4 pi is 0. So if I take even terms, then Cn would be 0. And if I take odd terms, then we'll have to see. So let's say if I take odd term, so let's say if I take n equals to 1. So if I take n equals to 1, this is sine 3 pi by 2. So this would be minus 1. If I take n equals to 3, so this will be sine 5 pi by 2, which is 1. So it will be alternatively plus minus 1. So Cn would be 0 if n is even. Okay. And it is equals to plus minus 4 root 2 divided by pi upon n square minus 4 uh, 4 root 2 upon pi upon n square minus 4 if n is odd. Okay, this is clear. Or you can write it as minus 1 raised to power n minus 1 upon 2 into 4 root 2 divided by pi n square minus 4. So if n is equal to 1, it was, I think 0 it was. So instead of writing n plus 1, I write, okay, if n was equal to 1, so 1 plus 1 was 2, 2 divided by 2 is 1, so minus 1, okay. If n was 3, 3 plus 1 is 4, 4 divided by 2 is 2, minus 1 raised to power 2 is 1. So clear? So either you write this way or you write this way, these are both same things, okay. So what is the, another case was if n was equal to 2. So if n was equal to 2, so I can write integral 0 to a root over 2 upon a sine pi x upon a, and then again root over 2 upon twice a, and then sine of uh, n pi x upon 2a. Na? So n is 2, so this will remain this only, dx. Okay, if I place n equal to 2, you remember in the new ground state, the new states would be root over 2 upon 2a sine of n pi x upon 2a. So if I place n equals to 2, it will give me pi x upon a. Okay, so that is fine. So if n is equal to 2, then I'm getting integral 0 to a. This will be, I think, root over 2 upon a, and simply sine square pi x upon A dx, and this you can find on your own. This will be equals to I think A upon 2. Okay, this will be A upon 2. So root over 2 upon A into A upon 2, I'll get 1 over root 2. So finally, we have calculated this coefficient Cn. The Cn would be equals to what? It will be 0 if n is even, except 2, sorry. I was not supposed to take 2 here. So kindly, so this n equal to 2 will not come here because n equal to 2 was a separate case. So I apologize for the same. And if n is equal to 2, then it will remain 1 over root 2. And otherwise, it is plus minus 4 root 2 upon what? 4 root 2 upon pi n square minus 4 when n was odd. Okay. So what would be Pn? So probability of finding the particle in different these states, different states, like if I'm in now new ground state, it would be psi 1, which is equal to root over 2 upon 2a sine of pi x upon 2a. If I'm in psi 2, so on and so forth. So what would be the probability corresponding to this? It would be C1 mod whole square. What would be the probability corresponding to psi 2? So psi 2 is this. The probability of finding the particle in the new uh, well in the state psi 2 would be simply 1 over root 2 whole square. So Pn is what it is, Cn mod whole square only, and it would be equal to 0 if n is even, except 2. Okay, n should not be equal to 2. If n is equal to 2, then it is equals to 1 over 2, and it is equals to 32 upon pi square n square minus 4 whole square if n is equals to 1, 3, 5, so on and so forth. So what do you think the most probable state would be? So you can find the probability, like if you place n equals to 1 here. So if n is placed 1 here, it will be 3 ka whole square, which is 9. 32 by 9 divided by pi square. So it will be less than 1 by 2 anyway. So the most probable state, most probable state would be E2, which is simply uh, pi square h cat square upon twice m 2a whole square. So it will give me what? It will give me pi square h cat square upon twice m square. So I would be in the state E2. I would be in the state E2, no doubt, but the energy remains the same. So if you remember, I was initially in the ground state of this potential well of width A. Okay. And initially the energies was what? Initially the energy was pi square h cat square upon twice m square because I was in the ground state. Now, uh, the most probable result turns out to be this 1 over root 2. If you start placing these values of n, you will find that the probability is less. So most probable result would be corresponding to E2. However, the energy measurement comes out to be the same. That is 4 pi square h cat square upon twice m at twice a whole square. So this 4 cancels out. So we get the same energy measurement as that of the previous ground state. So this is something that you have to remember. And what is the probability of finding this energy? The probability of finding this energy would be simply 1 over 2. Okay. So now question arises, what would be the next most probable state? So what is the next most probable state? So what is the next most probable result, I would rather say. Okay. This is 0, this is 1 upon 2. So next most probable result would be obviously because n is equal to 3, as n keeps on increasing, this will decrease because n is in the denominator. If n increases, then this will decrease. So most probable result you will find corresponding to the energy state E1. And what would be E1? E1 would be pi square h cat square upon twice m twice a whole square So energy would be pi square hk square upon 8 ma square. So the next most probable result would be corresponding to the energy values pi square hk square upon 8 ma square. And what would be the probability of obtaining these energy values, that is even? This would be, I think, 32 divided by pi square. And I think so. This I think I'll get 9, right? So I'll get 9. So this would be the probability of obtaining the energy pi square hk square upon 8 ma square. Okay. What is the expectation value of the energy? So expectation value of energy will be what? So I'm leaving this particular portion to you for you to answer. So expectation value of energy, I can write it as integration from 0 to a psi star h cap psi dx. Okay. So what is the expectation value of energy? And so this will be psi star h cap and psi dx. And this you have to calculate. Okay, this you have to calculate. I'm giving you this as a homework. Try to do this, and you will be surprised to know that this comes out the same even when the wall was not removed. So if wall was removed, uh, wall was not removed. So that particular case, if you want to find the expectation value of energy, and if wall was removed and doubled now, and now if you find the expectation value, they remain the same. And I'm leaving it to you as an exercise. The value will turn out to be equals to pi square hk square upon pi sigma square. If you want to find it using Cn En, that also would work. That's not a problem. So Cn mod whole square En, but this will really be a little difficult because you already know that Cn is slightly complicated. So it's better that you take this approach. It's better that you take this approach and try to find the expectation value of the energy. What is more surprising that I want to really draw your attention to, this value will come exactly the same as before the wall was moved. So basically, if wall was not moved, and even if the wall was moved, there would be no change in the expectation value of the energy. This I'm leaving it to you as a homework. Try to do it. Otherwise, I'll give you the answer in the next class. Now, just for consolidating this concept, let us now think, what if the wall was now quadrupled? So initially, let's say the width of the wall was was a, and now the width has been changed and it has been quadrupled. Now it is made 4a. Okay, and let us assume that initially we are talking of the ground state. So let's say initially it was in the ground state, and instantaneously the width of the wall has been increased from x equal to a to x equal to 4a. Now let us be precise and let us ask a few questions. We have done it in the most general fashion above. Let us now ask, what is the probability? What is the probability of finding the particle A in the ground state of the new box, and B in the first excited state of the new box. So let us try to do this question, and which will consolidate our concept. This I'm leaving you as an homework because this will become a long integral to do. So I'm leaving it to you. I hope you'll be able to do it. If you're not able to do it, I'll do it for you. But even if you can do this also, it's fine. But please do remember, this is going to take a little bit. It would be a very difficult thing for you to do right now with an infinite series. So it's better to go with the integral way. Okay. So now let us focus our attention onto this. So we have now quadrupled the width of the well. And now we are asking that what is the probability of finding the particle in the ground state of the new box and in the first excited state of the new box. So we know that initially the particle was in the ground state. So initial energies were pi square hk square upon twice ma square. And what was the initial it was placed in ground state. So I'll write root over 2 upon a. Okay, root over 2 upon a. So psi I initially was root over 2 upon a pi x upon twice a. So pi x upon a, sorry. Now, if I quadrupled the width of the well, so in the final, now after this transformation has been done, so now what would be the wave functions? The wave function would be root over 2 upon 4a sine of n pi x upon 4a. And now we precisely want to know what is the probability of finding the particle in the ground state of the new box. So what is the ground state? It would be corresponding to n equal to 1. And what would be the final energy eigenvalues? It will be n square pi square hk square upon twice m 4a whole square. Okay, so these are the new energy eigenvalues for the new box. So what is the probability of finding the particle in the new ground state? So what is the ground new this will be psi I psi mod whole square. And I know what is the probability of finding the particle in, what is the what is the wave function? So it will be root of 2 upon 4a, and this will be sine of pi x upon 4a. So we have to place n equal to 1, which would be corresponding to the ground state of the new well, into root over 2 upon a sine of pi x upon a dx. This mod whole square. So what we'll get? We'll simply get uh, the 2 upon 4a whole square. I think this is root 2 upon a, sorry. So this is, sorry, simply 1 upon a square, root 2 upon a, right? So this is root 2 upon a, 2, 2, 4, 4 cancels out. So it is equivalent to finding this integration, 0 to a sine pi x upon 4a into sine this whole square. Okay, this is one thing. And you know, from the relation, you can write this as cos a minus b minus cos a plus b. So I can multiply with 2 here, and I can multiply with 1 upon 4a square outside. Okay. And please do remember why I have taken this a only. See, why I have taken this a only? Because remember, when I was talking of initial wave function, psi I, it is equals to what? Root of 2 upon a sine of pi x upon a. So initially it was in the ground state, but remember, this particle remains confined from x equal to 0 to x equal to a. From a to 4a, here the wave function is 0. So it's not going to yield you anything. So therefore, the upper limit I have constrained it to a only. I am not writing it as 4a. And similarly, here also the same thing. Because you see, beyond a, you also know that the wave function would be 0. So if I'm integrating from a to 2a, the, this wave function will be still there. That is root over 2 upon 2a sine n pi x upon 2a. But this wave function would become 0 for, for the values of x lying from a to 2a. So therefore, the integral limits remains from 0 to a only. Effectively, that is only going to contribute. So I hope this is clear. And this is equal to what? 1 upon 4a whole square. And this integral would be what? This integral would be integration from 0 to a cos of a minus b. So this is 1 minus. So this will give me cos of 3 pi x upon 4a minus cos of a plus b. This will be 5 pi x upon 4a. Okay, mod whole square. Now, if I integrate this up, I'll get 1 upon 4a square modulus, and cos is sine, so 4a upon 3 pi sine 3 pi x upon 4a minus 4a upon 5 pi sine of 5 pi x upon 4a, and I have to take the limits from 0 to a, and this mod whole square. You know that if I place 0, lower limit would be 0. If I place upper limit, then I have something to do. So finally, I will get 1 upon 4a square, and this 4a would come out. So this will be like 16a square. This is fine. If I place a here, what I will get? I will simply get 1 upon 3 pi here, sine of 3 pi upon 4 minus 1 upon 5 pi sine of 5 pi upon 4 whole square. If you remember, what is this? This is sine pi plus pi by 4. So this is minus 1 upon root 2. So minus minus becomes plus. And this is 1 upon root 2. So this is 16a square upon 4a square 1 upon 3 pi 1 upon root 2 plus 1 upon 5 pi into 1 upon root 2. And this mod whole square. And this I'll get, I think this is quite evident. I will get 4. Simply, I think this cancels out. I'll get simply 4 here. And this will be like root 2 here. Not root 2, I think pi root 2 if I take common out. So 1 upon pi root 2 if I take common out. This will be 1 upon 5 plus 1 upon 5 plus 1 upon 3. It will be like 15. I'll take an LCM. 5 plus 3. I think this is quite clear. So now this is equal to 4 upon pi square into 2 into 8 square. Is that 8 square? 8 square divided by 15 square. And what is 8 square? 8 square is, I think, 64. And this 2 cancels. So 64, 32. So this will, I'll get 128 divided by 15 square and divided by pi square. So if I calculate, this comes out close to 0.058. So there are 50%, 58% chances that when well is shifted, that when the well width of the well is shifted from A to 4A, the new ground, the particle would be in the new ground state. So for particle to be in the new ground state or ground state of the new box, how much percentage chances are there? There are 50%, 58% chances are there. Now next question that is asked is, what is the probability that we find it in the first excited state of the new box? Okay, so I know what is psi initial. Psi initial was root 2 upon a sine of pi x upon a, and psi final was equals to what? So first excited state corresponds to n equals to 2. This is root 2 upon 4a sine of n pi x upon 4a. So this is like psi final is 1 upon root 1 upon 2a sine pi x upon 2a. So this is what it is. Okay. Now, what is the probability of finding the particle in the first excited state of the new box? It will be simply this psi final, psi initial. Okay. And this is equivalent to writing 1 upon a square integration from 0 to a sine pi x upon a into sine of pi x upon twice a dx. If I multiply 2 here, I multiply 2 here, and this mod whole square. I hope you're going to find this integration. And this integration turns out to be equivalent to 16 upon 9 pi square, and which is almost equal to 0.18. So there are 18% chances that the particle which was initially placed in the ground state in a well with bit A now goes into the first excited state of the new box, where new box is the box which has the bit 48. So how much percentage chances are there that now particle is in the the particle goes in the first excited state, or particle is present in the first excited state, or we get the energy eigenvalue as E2. That is the first excited state corresponds to the energy eigenvalue E2. So there are 18% chances. So I hope such questions you will be able to now tackle. So in exam, we are going to see all these things later also in perturbation theory. But right now, just for the sake of doing it, I have explained the concept, and I have done a small problem also. Such questions are asked in examination, so you really need to pay attention to these problems. I hope you're getting benefited by the lectures. If you have any doubt and difficulties, kindly let me know in the comment section. Till then, take care. Bye-bye.